All right, perhaps you took a look at the screencast for the multiple choice. This will be the free response for the Chapter 9 and 10 test review. The first question, question number 13 here, we're looking at the proportion of cars that are red, and nationally that's 12%. And a Phillies fan who likes red cars wonders if they're more likely to drive red cars in Philly. So during a home game, he takes a simple random sample of 210 cars parked at their ballpark and counts 35. So 35 successes out of and 210. And there are a lot of parking spaces, so we're feeling good about independence here. Is there convincing evidence that they prefer red cars than the general population? So I'll number this, my 4-step plan, 1, 2, 3, 4. You don't need to do that. But things that need to be included are a null and alternative hypothesis. The null, we'll say nationally, is 12%, versus we're looking to see if it is greater than 12% nationally. And then we'll define P, which is the true proportion of red cars in the lot. Because that's where the sample was taken from, was in the parking lot. And so the estimate really can be then only applied to the true proportion of cars in the parking lot, and then the inference you want to make beyond that, that everyone in the parking lot is a Phillies fan and so on, it's for you to decide. But as far as what does P represent, well, it can only represent the true proportion of cars that are red in the parking lot, because that's where the sample came from. And that's step 1. Maybe this would be a good time to establish an alpha of 0.05, because we weren't otherwise told. And I think we're all pretty comfortable choosing that as our baseline alpha level. In order, we got to check some conditions for the 1 prop Z test. There we go. The 1 prop Z test by name or by formula, which is a Z test. Whoops. Z equals P hat minus the null P over null P, null Q over N. Now remember, it's the null P and null Q because of the hypothesis. We're stating that we think it is 12, therefore the standard error, the standard deviation of the statistic ought to use that. But either by name or by formula. Now in order to do this test, we need to check our conditions, which is random, independent, and normal. And it was stated that it was an SRS, so we'll go ahead and put that. Independence, let's see, 21,000 spaces, which makes us think that there's at least 10 times at least 10 times the sample in our population. So independence has been met. And then for the normality, make sure that we show the numbers here. And it's NP, again, it's the null P, and NQ. NP, which is, let's see, 210 times 0.12, 25.2, and then 210 times 0.88 is 184.8, both of which are greater than or equal to 10. So we're good. All the conditions have been met, and we've stated as much. Step 3, and I'll truncate this at some point, but give myself some room. This is where we are going to do the work. And P hat in this problem, 35 over, whoops, that's 210. is 0.1667. At some point you can terminate the decimal, but the test, z equals 0.1667 minus 0.12 over null p, null q over n square rooted, gets us 2.081. That's the z-score. And then the probability that we get a z that's greater than 2.081 is equal to, looking up on our table or normal CDF, however you want to find it, in the neighborhood of 0.187. That's our p-value, is 0.0187. And that's all the work for step 3. So step 4, the conclusion, is we are going to decide that we are going to reject the null because the p-value is less than alpha. And you want to make sure that you state that that's why you are rejecting the null, is that the p-value very specifically is less than the alpha level, and when the p-value is low, reject the ho. And we conclude that there is convincing evidence that the true proportion of red cars at this ballpark is greater than 0.12. Right? You don't need to interpret the p-value unless specifically asked to, but what it is it is the likelihood that we would have gotten this proportion of red cars or more if in fact the true proportion is 12%. So if there's really truly 12% in the parking lot, the likelihood we would have gotten 16.67% just by chance, we would have tripped into it just by dumb luck, is less than 2%, which is so unlikely that we say, okay, maybe more likely something else is going on. Question 15 didn't give us a ton of space to carry out this test. That's okay, we'll tuck it in. Let's see. Researchers explained commonly held belief between a normal night's sleep and 2 nights of, quote, extended sleep. Let's see. We have subjects, and they are getting normal and extended sleep. So each subject's going through 2 things. Hopefully you're thinking to yourself this categorical variable of subject number and their vigilance scores. This is looking like a paired situation. And we're looking for the difference. So we'll maybe sneak those differences in there at some point. Drag that up. I might want that space later. But we're going to test the average difference. So the null is mu sub d is equal to 0. The null is that there is no difference, versus the alternative is that it does, that the score is higher for extended sleep. So extended minus normal would be a positive test. So mu sub d equals the true mean difference in vigilance score. We'll say extended minus normal for similar subjects. Right? So it's not for these subjects, right? We're talking about the true difference among these types of subjects. So however it is that these subjects were chosen, groups similar to them, is the true parameter that we're estimating here. It's not the sample. You could have done a less than problem if you want to subtract the other way, but I think typically, well, I guess there's really two things. A lot of people will want to subtract downward, looking at these differences. I mean, those happen to be 0 either way you cut them. But I've chosen to go extended minus normal to get a difference of 3, a difference of -2, a difference of 9, 5, 6, 12, 7, and then -8. That's how I chose to do it, just to keep the difference. The average difference is going to be positive, and for whatever reason, I like having a positive score. Specifically with means, a positive t-score, that's what my table gives me, so that kind of makes some sense. But if you wanted to subtract just down that way, it would have been a less than problem. So that's up to you. Not given an alpha level, we'll say 0.05 again. I think people are okay with that. We'll tuck our conditions in. Well, excuse me, the name of the test. This is the paired t-test for means, or whatever you want to call it, the one sample t-test for paired data, paired t-test. As long as I think paired and t-test come together, we'll be fine. We've said that it's means, so but paired t-test are the big deals there. You could also say that t equals x bar, well, I guess I did capital D, minus mu d over the standard deviation of the difference divided by the square root of n of the difference. So let's see, we've got how many of these? 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got 10. N equals 10 in this problem. We'll need degrees of freedom later, which is 9. So that's what we've got going on for us. Let's see, the conditions: random, independent, and normal. I'm going to run out of space. Let's see. At some point, hopefully this was stated that it was random, they were assigned in random order, and because of the, if it didn't explicitly say that, assuming that's how it was done, it's probably not, a tragic assumption to think that that's how that happened. So random assignment, which was stated but could have been assumed. Let's see, independence. So it is dependent, right, from normal to extended, but subject to subject is independent. And so this wasn't a random sample, so we don't want to use the 10% rule. We just want to say that the vigilance scores are independent subject to subject. And that's as best as we can do. And that really does get taken care of by the random assignment, if you want to attribute it to that. But definitely not saying 10% rule would be important for that statement. And then normal, I'm not told that they're normal, and n is only 10, so it's going to fall on me to investigate what's going on with some sort of picture. And given the space I have here, and without punching things into my calculator, let's see, if I go -10, -5, 0, 5, 10, I'm just going to make a dot plot for the simplicity of it all. -8 was my lowest number. I had a -2 on the board, a couple zeros there. I have a 3 on the board. Let's see, 5 and a 6. Let's see, 7 there. And then, what's my other one? 12. I have a 12 there. And an 8, 7, no, 7, and that was a negative 8. So 5, 6, 7, there we go. Do I have them all? And a 9, looks like. So I think we're looking pretty good. I've got all those in the right spots, I hope. Now there's only 10 observations. I've got a little peak right there in the middle. Only 2 observations to the left, a bunch of observations to the right. No dramatic skewness. Based on what I see, I'm not sweating this too much. If you were worried, maybe you go a little bit farther and make sure this guy's not an outlier, but I think we're looking okay to do this. Evidence. Well, let's say no evidence. Right, we're not confirming anything. No evidence of non-normality from the dot plot. So we want to make sure that we include that. We can't just say it, we want to include it. But all the conditions are met, so we're looking pretty good here. So I will need to fire the data into my calculator real quick just to make sure that we've got X bar, which I haven't collected yet. And probably would have been a good idea to do this and then graph it, but I have X bar at 3.42. And then the other thing that you could do that might be worth your time is, if you're going to put the data in your calculator, then you can put this in L1 and this in L2 and do the subtraction, those column operations to get that there.